So thank you. Yes, so unfortunately, Robert, he's at home with the flu. He can't make the conference at all, so he asked me to step in for him. He gave me the slides this morning, so let's see how this goes. But I think I know enough about the connectors to also give a pretty good overview of what is going on in the world of connectors and in Flink. So in this talk, we're first going to have a look at the available connectors and have a look at the features of these connectors. Then we're going to have a more in-depth look at the Kafka connector, which is, I would say, the most important connector for Flink because almost everyone is using Kafka, and you can use Kafka as a generic interconnect and also put other data into Kafka and read from Kafka. Then we're going to look at, in the context of Kafka, we're going to look at how end-to-end exactly once in Flink can work, because that's quite interesting, and Flink has some novel ideas there that other systems don't have. Then we're going to look at Apache Bahir, which is a somewhat new project in the Apache space that is a cross-project for connectors. So there's some connectors for Spark in there, some for Flink. We're going to have a look at that in more detail. And then, if we have time, we're also going to look at message queues, so ActiveMQ, RabbitMQ, and how Flink works with them to provide exactly once messages or at least once messaging guarantees. So that's the current state of connectors in Flink 1.1. And for each of the connectors, there can be a source or a sink. So source is for reading from that special data store, and a sink is for writing to that data store. So let's go quickly through the available connectors. So for reading from files, that is from HDFS, or for reading to files, there's the rolling sink or the bucketing sink, which we're going to have a look at. Oh, by the way, we're also going to have a look at whether the source and the sink they provide exactly one semantics or not. Because some sources, due to the nature of how they work, they cannot really provide exactly one semantics when reading from them, only at least once. Or some don't provide guarantees, but for files, we have exactly once guarantees. Then, of course, there's Apache Kafka, where we have a source and a sink, Kafka consumer and a Kafka producer, where we provide exactly once for the sources, but not for writing to Kafka, because having exactly once across a program, reading from Kafka, writing to Kafka, would require some cooperation, I would say, from Kafka, which it doesn't yet provide, but apparently they're working on that. Same goes for Amazon Kinesis, which is more or less a similar thing to Kafka, so also a message queue with some different semantics, and we can also read and write from Kinesis, and also only provide exactly one semantics for reading from Kinesis. Then another type of message queuing systems is RabbitMQ and ActiveMQ. These are not log-based message passing systems like Kafka, but really element-based, acknowledgement-based message passing systems. And for these, we also provide sources that provide exactly one semantics, but not sinks that provide exactly one semantics. Then let's move on to a class of systems for which we only provide sinks. So these are Elasticsearch and Apache Cassandra. Both of them are, the rough idea of them is that they're key value stores, and Flink can write to them, but for Elasticsearch, we provide no guarantees with respect to if the data gets there or if we do duplicate writes. And for Cassandra, we provide exactly once guarantees with the restriction that the updates that you are writing to Cassandra are idempotent. That is, if you do an update several times in a row, this should still be the same result. And then we provide exactly once guarantees. And then there's two systems for which we apparently provide no guarantees. So that's Apache NiFi, which was offered to the Apache Foundation by the NSA, I think. So there you go. It's also a system for stream processing, and you can also read and write from Redis, which is an in-memory key value store, but there we also don't provide guarantees. So let's look at the streaming connectors by activity. So in the parentheses, you see when we added support for this specific connector. And what is obvious is, what I also mentioned in the beginning, is that the Kafka connector is by far the most important connector of Flink. So most of the questions are being asked about Kafka, but we also provide support for Kafka since 0.7. So the next interesting data point is Cassandra, for which we only provide support since Flink 1.1, so the last version. But we already have 38 emails on the mailing list that mention Cassandra. So Cassandra seems also to be a very heavily used thing, or the users seem to be interested in Cassandra. Then next we have Elasticsearch, some mentions, the file sources, and then most of the other things are not that sought after. So Kinesis has been picking up a bit lately. So the message log system that you can only use in Amazon. So we have recently added support for reading and writing in Flink 1.1, and there also seems to be some interest. But in Apache NiFi, not so much. So maybe people are afraid that the NSA might be listening, and I'm not sure, but that's the state. So let's move on to a more in-depth look at the Kafka connector. So first, so that we're all on the same page, what Kafka really does. So what it is a message passing system. So you have your cluster of Kafka nodes sitting there. You can have producers that write data to Kafka, and you can have consumers that read in parallel from Kafka. And the basic building blocks that you have in Kafka is a topic. So if you want to write somewhere, you have to first create a topic, and the topic is basically a named stream. So you can have a topic, for example, for user, events, or sensor data, and so on. And a topic can be further partitioned into partitions, which provide some level of parallelism for a topic. So here in this example, we have a topic that has 3 partitions. So this allows to spread the data across the different nodes in the Kafka cluster, and also allows to read the data in parallel, because the number of parallel readers that you have for one Kafka topic is also bounded by the partition. And how it works in Kafka is that you can only append data to a Kafka partition of a topic. This is where the write position is, and this can be different across the partitions. You see this over there. And then readers, they can read from a topic, and then they would have a read position. That's basically how Kafka works, or what Kafka provides. And now we're going to look at how Flink deals with Kafka. Because the interesting thing is that Flink has essentially 2 implementations for the Kafka connector. So between Kafka 08 and Kafka 09, there were some changes in the Kafka APIs. And Flink, when reading from Kafka 08, is using the simple consumer API, which is a more low-level API for Kafka, where Flink itself has to do a lot of working with the simple consumer API to make sure that we get exactly one semantics and that we correctly commit offsets, which we're going to get to in a second. And then with Kafka 09, they introduced a new Kafka consumer, which is taking a lot of the stuff that programs reading from Kafka previously had to do themselves if they were using the simple consumer. For the producer side, so writing to Kafka, nothing really has changed between Kafka 08 and Kafka 09. So let's look first at the Kafka O8 consumer. So you have there on the top, you would have your Kafka cluster sitting, and in Kafka, the nodes that store the actual data, they're called Kafka brokers. And Kafka brokers, they would be responsible for numbered partitions in a topic. So in this example, we have two topics, topic A and topic B, and they each have a number of partitions. So you, for example, see that the broker on the upper left, it has partition 2 of topic A, and it has partition 0 of topic B and partition 0 of topic A. So that the load is spread out across the brokers. So as I said, on the top is Kafka, and on the bottom is Flink. And how Flink is set up is that there is one consumer thread per task manager, and then inside this task manager, it spawns one fetcher thread per broker from which this Kafka source is reading. So in our example, the task manager on the left, on the lower left, would be reading from the broker on the upper left and from the broker on the upper right. So it has two fetcher threads, and these fetcher threads are responsible for the topics that are stored in this broker. So that's the basic setup of the Flink O8 consumer. So it's a bit complicated because Flink has to do all the management of these consumer threads and the fetcher threads, and also some other stuff when it comes to failure. So Kafka can of course fail. So if a broker fails, the Flink source reading from Kafka has to switch to a different broker. And this has to happen dynamically so that the job doesn't fail. So what would happen is, in this example, our consumer on the lower left is reading from this broker here. This fails, and then this fetcher thread notices that reading from this broker fails, and it would return these partitions from which it is reading. So these topics, it would return these to the consumer thread, and then the consumer thread would be responsible for spawning a new fetcher thread and spreading out these topics that they're reading from to other fetcher threads. So what happens is that it spawns a new thread, so this new fetcher thread, and then it redistributes the work of reading from these topics to the existing threads. So in this case, it had 3 topics that it had to redistribute to fetcher threads, and what it did is it put one of these topics on an existing fetcher thread, and it put 2 topics on this new fetcher thread. So this might seem very complicated because it is. So the basic idea is that you should get from this is just Flink reading from Kafka O8 is quite complicated because the Kafka APIs at that time, they were not really very nice to work with. So unfortunately, this has changed with the Kafka O9 consumer. So with the Kafka O9 consumer, basically what you're doing is you have these brokers sitting up there. You just create a consumer for consuming from some topics in from some partitions in some topic, and then Kafka does all the magic of rebalancing when brokers fail, making sure you commit the right read offset to other things, and so on. So that's pretty nice. And hopefully once Kafka O8 is deprecated and no one is using it anymore, we can get rid of the code that we have for the Kafka O8 consumer. So now let's look at how Flink provides exactly one's semantics for the Kafka consumer. And so we're going to look at this in the context of the Kafka consumer because this is the most prominent consumer. But how Flink provides exactly ones is not specific to the Kafka consumer, but is a general thing. So let's dive in. So the setup we have is this. We have basically 2 partitions in our topic that we're reading from. We have 2 Kafka consumers, and we have this map operator. And then what we also have is how Flink checkpointing works is that there's a Flink checkpoint coordinator which periodically sends requests to do a checkpoint to the Flink operators, and then they do checkpoints and they propagate barriers to downstream operators, which in turn tell them to do that checkpoint. So that's the Flink side on the right, and this so the checkpoint coordinator and these sources. And then there's also something in Kafka or Zookeeper, where a Kafka consumer can store the offset from which it is reading in Zookeeper, so that external systems can learn the read position of a consumer, or so that you can, for example, stop the job and start from a certain position stored in Zookeeper. But Flink would work without storing these offsets in Zookeeper, because Flink uses Flink checkpointing to keep track of where we are in Kafka. So let's walk through an example. So what happens is the first consumer reads this element A, and then the offset at that consumer switches to 1. So up there you see the offsets. So it was 0, and now it is 1. Then it sends that element downstream and reads the next element B. So now the A arrived at that map operator, which is counting the elements that it saw. So the counter goes up to 1. And concurrently, the upper Kafka consumer consumed the B. The lower one consumed the A. So the read offsets at that point are now 2 and 1. And at this point, for some reason, the checkpoint coordinator decides that we should do a checkpoint. So what happens is it asks the sources to do a checkpoint, which they do. So in the checkpoint coordinator, we see that we have checkpointed the offsets 2 and 1. And the Kafka consumers also send these barriers to the downstream operators. So these are the barriers. And if a downstream operator receives barriers from all the input operators, then it would itself do a checkpoint. So at the downstream, this operator that does the counting has seen the B, so it does the count to 2. It has seen the other A from the lower consumer, so it counts to 3. Then it sees the barrier and also does the checkpoint. So at that point, we have a completed checkpoint where we read where the offset or the read position was 2 for the upper consumer and 1 for the lower consumer, and the count that is consistent with this is 3. Because if you think about it, if we have offset 2 here, offset 1 here, we should have seen 3 elements, and 3 is the count that we have. And you will also notice that while we were doing the checkpoint and this asynchronous checkpoint was passing through the topology, Kafka read some more elements which were in flight while this checkpoint was going on, but they are not reflected in the checkpoint state, because the checkpoint has to be a consistent view of some state. And then once the checkpoint is complete, the checkpoint coordinator will inform the sources that the checkpoint was in fact complete, and at that point they also write these read positions to Zookeeper so that external systems can learn about this. And then once this whole checkpointing business is over, we just keep processing, so they read some more stuff, and then, oops, we have a failure. So at that point, what we have to do is reset all the operators to a state that we previously checkpointed. So the state that we have was offset 2, 1, and the count of the counter was 3. So what we do is we reset back the read position, we reset back the counter, and then we can continue normal processing. So I'm sure that's a lot to take in, because it also goes into details how exactly the Flink asynchronous checkpointing works, which in my opinion would be worth a whole talk of its own, but you can ask questions about this afterwards, I'm sure. We might have some time. Uh-huh. Yes, so for example, if you use Kafka in production, you might want to know if your Flink job or your readers are keeping up with the data coming in. So you have the data coming into Kafka, you see what the write position is, and if you know the read position, that is the position that the readers are reading from, you know if they're lagging behind the write position. So this would be helpful. That's why Flink puts the read positions also in there. So let's move on to end-to-end exactly ones. So what this means is that we have a source, we have a Flink program, and we have a sink, and we provide exactly once processing guarantees in case of failures, so that the data that we have there should not be duplicates, or it should look as if no failure ever happened. And as I mentioned earlier, this is not possible with Kafka because of some restrictions in how you can write to Kafka, but it is possible with some other combinations of sources and sinks. So, for example, if you use the file monitoring source, which is down there on the left, then we can provide exactly one semantics to read from files, process them, and write to files with the rolling file sync, which would be the equivalent to reading from files, and the rolling file sync is writing to files. And as I mentioned earlier, if you use Cassandra and have idempotent updates, then we can also provide exactly once guarantees if you read from Kafka or from some of these other systems. So because that's a bit of an interesting thing, the file monitoring, I'm going to go into some details how that works. So the file monitoring source is actually a source that is split up into multiple operators. So what you have is, you have here some file system, the green barrel, maybe. This could be HDFS, and then the blue boxes, they're the Flink operators that are required for reading this. So we have there the monitoring task, which is responsible for monitoring, for example, some directory and checking if there are new files coming in. And then when it sees a new file, it would send a data item downstream to these parallel read operators. And what it sends is, for example, it sends a file path and an offset where this reader should read from to this read operator. So if there's a new file coming in, it can split this into chunks and send downstream these file path offset pairs, and then these parallel read operators, they would be responsible for reading the data from the file system and emitting the actual contents of the file downstream so that they can be processed. And when checkpointing, that's the interesting bit here, you just have to make sure that you checkpoint the files that are currently there and the offsets that you have read from them to make sure that you have a consistent view when you do checkpointing. And then the other side of files, so we saw file reading, now we have file writing, is the rolling sync or the bucketing sync. The bucketing sync is the more generic version of the rolling sync. So what this provides is you have a stream of incoming data, and you can write this in buckets into the file system. So you could, for example, write this based on time. So you would have one file from 8 o'clock, then the next file from 9 o'clock, so that your downstream systems can again read these files, because you don't want to have one continuous file that you never finish writing. You want to split them into some manageable buckets. And an interesting thing of the bucketing file sync is that you can also bucket the data based on some property of the events that you're writing. So you could, for example, based on the prefix of some string or some number, you can put them into buckets. So here we have bucket for some data 0 to 4 and some data 5 to 9. So that's something that is interesting to a lot of people because they asked about this. And this is actually a community, the community developed this bucketing operator. Someone who wanted this functionality and provided it and was kind enough to give it to Flink. And another interesting thing in the bucketing file sync is that in Hadoop 2.7, there was a new feature called truncate, which allows you to because before 2.7, Hadoop would only allow appending to files. But with Hadoop 2.7, it would also introduce this new truncate call, which allows you to cut off data from the end. And why this is interesting is if you write files to HDFS, and if you have a failure in between, then you need to make sure that when you restore, you also need to roll back what you have already written to the file system. Otherwise, you might see duplicates in the written data. So what you do if you restore from a checkpoint, you roll back the internal state. And if you use Hadoop 2.7, you also truncate the file to the data that was written at the point where the checkpoint was taken. Of course, not everyone is using Hadoop 2.7, so on earlier versions, we would recognize that the user is not using Hadoop 2.7 and then would write some special metadata with the file that would indicate to which offset the file contains valid data. So in this case, the user would have the burden of making sure that it only reads the file to that point where it contains valid data. But hopefully, once everyone is past Hadoop 2.7, that should be a non-issue. And then one last interesting thing about Flink and its connectors is, I mentioned this before, the Kafka does currently not provide features to make sure that data is written to Kafka, and it also doesn't provide transactional features. So you can't, as I said, in the file systems, you have to truncate the data. Once you write data to Kafka, you cannot take it back anymore. That's the reason why we cannot do exactly once end-to-end reading from Kafka, writing to Kafka. But once they provide transaction support, we can also do it. But for now, at least, we make sure that to make sure that data is written to Kafka, what we do is when we do a checkpoint, we keep track of the messages that we sent to the Kafka broker that were not yet acknowledged, and we wait for the count of unacknowledged messages to go down to 0, so that we at least guarantee that there's no data loss. But if you use Kafka, you can have duplicate data in your Kafka queue in case of failures. So that's it for a quick overview of the interesting features in the Flink connectors. So let's move on to Apache Bahir and also some future developments in the connectors. Because an interesting thing that is coming up is in Kafka 0.10, Kafka added support for timestamps in the data items. And of course, with Flink supporting event time, that's a natural fit. So we're working on also allowing data to be read from Kafka 0.10 with support for timestamps, and also for writing data to Kafka with the proper timestamps. And what we also want to work on is to add support for dynamically scaling the Kafka connector and other connectors. So that's a bit of a stretch. So if you saw some of the earlier talks, what we are talking about is that we want to allow to dynamically scale in and out the parallelism of Flink jobs. So job elasticity and cluster elasticity are the keywords here. And if we want to do this changing of parallelism, we also have to make sure that this properly works with the connector, so with Kafka or Kinesis and so on. So there's some work going into this direction to make sure that this is working properly. And we're also internally refactoring the Kafka connector API to make sure that, because right now, so there's some redundancy in how the Kafka connector works. So Kafka provides something they call serializers, which is you specify this, and then the bytes that are read from Kafka are transformed into your actual data. But Flink has basically duplicate versions of these serializers, and we want to make the Flink consumer behave more like or use the already provided features of Kafka, so that we reduce the complexity a bit there. This is also something driven by users. They have picked this up. And then, as I mentioned, this Apache Bahir. So Apache Bahir is a top-level Apache project that is quite young, that was started by members of the Apache Spark PMC, actually. So you might be wondering what Spark and Flink and whatever, but Apache Bahir is a project aimed at providing basically a community for writing connectors for platforms. So things like reading from ActiveMQ or some other stuff. So the Flink community decided to move some of the connectors also to Bahir. And the reason for that is that, or the hope is that Apache Bahir, with only being focused on the connectors, can have shorter release cycles and advance the connectors more swiftly than with the Flink release cycles, which are a bit slower. But for the important connectors like Kafka, Kinesis, and files, they will stay in Flink. And some of the connectors for Flink that we have in Bahir are some I mentioned already. So ActiveMQ and Redis I mentioned. There's a Flume sync, and there's also some more connectors upcoming. And the Bahir community and we at Flink, we are always very happy to have new connectors contributed to Bahir. So that's an interesting project to keep your eyes on. So this apparently is the time to ask me questions. So you should follow Robert Metzger, who provided this slide set, and you can ask him privately any questions at his email address if you have any questions, but you can also ask questions on the mailing list, and you can of course ask me now if you want. But thanks. Do we have a mic for questions?
I can speak loudly.
Yeah, I can repeat it for the recording or whatever.
What opportunity is there for Bahir for a connector to be shared between Flink and Spark? Or is it basically a repository for two fully independent implementations?
Yeah, so the question was whether in Bahir there can be generic connector implementations that share code between a Flink connector and a Spark connector, more or less. So the honest answer is I don't know, but I think the way Flink connectors and Spark connectors work is very different. So it might be possible to develop some shim or some piece of code that could be used to provide a layer of abstraction between Flink connectors and Spark connectors, and then provide connectors that work on both Spark and Flink. But I'm not sure if this is possible, because the way Spark and Flink do fault tolerance is very different. So Flink has these asynchronous checkpoints, and Spark relies on the fact that they're doing micro-batching and can just repeat a whole micro-batch if it fails. So, but to be honest, I'm not really into how Spark connectors work, so I'm not sure how possible this is. But this would be, I think, a nice direction for someone interested in this. Yeah, that's true. I don't know, it's not a satisfactory answer maybe, but...
I'm trying to understand the rationale for the community moving to that.
Yeah, so mostly it's for offloading some of the work from the Flink main repository, and also for allowing faster release cycles with a project that is mainly focused on connectors. Yes, please.
Are there any plans to actually create sync for DynamoDB? Are there any plans to create sync for DynamoDB?
I'm not aware of any plans, but I think the nature of DynamoDB is very similar to Elasticsearch and Cassandra. So I think maybe if someone knew the API of Dynamo and they looked at the Elasticsearch or the Cassandra connector, I think they could maybe in a day do a connector, but I'm not aware of any plans there. And also to get really fault tolerant and well integrated and tested, of course that takes more time, but I think in theory nothing would prevent you from doing such a connector.
More questions? In the back.
What about MongoDB?
I'm also not aware of any plans, but also I think because Mongo is just a key value store, like on the surface, like the other key value stores, it should be easily possible to do a connector. But I'm not aware of plans there. Because, so I think no one really asked about a connector for this. If they have a need, or someone has a need for this, then they will either do it themselves, or the Flink community might decide to do it. But so far, we haven't had many questions about MongoDB. It's the first I hear of it.
So about the file system connector, the sync side, I have a question about the supported file formats, the outputs. Do you support any files that can be read by Hive and Impera behind, like ORC or Parquet?
Yes, so for this rolling sync and the bucketing sync, there's actually a generic interface to plug in to do the actual data writing. And I think someone a while back generified this even more with the aim of being able to write to ORC and Parquet. So the code is either already there or in someone's private repository. But it was meant to be pluggable, to write different data formats, yes. Yes, please?
Missing SQL databases. Are they not used at all, or are they not requested from the community?
So I think, so to answer the second question, they are not really requested by the community, but I think using some tricks, because I think there's a JDBC connector for reading and for writing, so you could use this also with the streaming API with some tricks. So this should be possible with some work.
I have a quick reply to this. Yeah, JDBC connectors there is, and it's like generic JDBC, so I was using it with Postgres, and now probably like works quite well.
Community at work. Thanks.
Some more questions? No? Ciao. Okay, that's it. Have a round of applause.
Cool, thank you.